Welcome to The Explainer. Today, we're going to tackle one of the most mind-bending, counterintuitive, and frankly, just weird ideas in all of science. It's the idea that everything from a tiny little photon to a baseball is actually exploring every single possible path through the universe all at the same time.
Look, I have to be honest. For pretty much my entire life, I believe that if you throw a ball, it follows one single, clean arc through the air. I mean, it seems obvious, right? You can see it. But it turns out that simple, intuitive picture of the world, it's an illusion. And it's one of the most convincing illusions that nature has ever cooked up.
All right, so to start chipping away at that illusion, let's begin with a really simple thought experiment. This is where we first start to see the cracks in our everyday intuition. I want you to imagine you're a lifeguard on a beach. You see someone in trouble out in the water. So what's the fastest way to get to them? Your first instinct might be to run in a perfect straight line. But here's the thing. You can run way faster on the sand than you can swim in the water. So maybe it's actually quicker to run a little farther down the beach first, to shorten the distance you have to swim, even if the total distance you travel is a little bit longer.
The truly fastest path, the optimal path, is always a compromise between running and swimming. And what's so cool about this is that light does the exact same thing. You've seen this a million times. When a beam of light hits water, it bends. And why does it do that? Because it's taking the fastest possible route between 2 points, not necessarily the shortest one.
So this brings up a really strange question. You, as the lifeguard, you can look at the situation and figure out the best path. But a beam of light, it doesn't have a brain. How does it seem to know its destination ahead of time and calculate the quickest route? It's almost like it's sniffing out all the possible paths beforehand. And that little puzzle, that's our doorway into a much, much deeper reality. To really get how light knows where it's going, we've got to jump in a time machine and go back to the late 19th century. This is a time when a really practical problem in Germany accidentally broke physics wide open. So back in the 1890s, electric light was the hot new tech. Germany was looking to upgrade its gas street lamps, and that meant they needed to figure out how to get the most light possible out of a hot little filament. To do that, scientists needed a solid theory to describe the light coming from hot objects, something we now call black-body radiation.
So, the greatest physicists of the time took the classical laws of physics, the stuff of Newton and Maxwell, and they used them to predict what the light spectrum from a hot object should look like. They were super confident they had this nailed. But when they actually measured it in the lab and compared it to their theory, oh boy, there was a big problem.
Their theory worked perfectly for long wavelengths of light, like red and infrared. But as they looked at shorter wavelengths, heading towards ultraviolet light, the theory predicted that a hot object should be blasting out an infinite amount of energy. Now that's obviously wrong. Your fireplace isn't emitting infinite energy. This epic failure became famous as the ultraviolet catastrophe, and it meant classical physics was fundamentally broken.
The solution to this mess came from a physicist named Max Planck, and he came up with a revolutionary idea that, honestly, he didn't even really believe in himself.
Planck, in what he later described as an act of desperation, basically just tried a weird mathematical trick. He said, what if energy can't just be emitted in any old continuous amount? What if it could only be released in these tiny, discrete little packets, or quanta? And the energy of each little packet, he said, was tied to its frequency by this now famous equation, E equals hf.
And wouldn't you know it, this little trick worked perfectly. It completely fixed the ultraviolet catastrophe. But to do it, he had to invent a new fundamental constant of nature, this little h, which we now call Planck's constant. And here is the giant clue that would change everything. The units of h weren't energy. They were the units of something called action. Now, just tuck that word away in the back of your mind. We're going to come back to it.
Planck honestly thought he'd just found a clever little workaround. He had no clue that he had just lit the fuse on the quantum revolution, a revolution that was about to completely rewrite our definition of matter itself.
Planck's idea just started to snowball. A few years later, Einstein came along and said, hey, what if light itself is made of these little packets, these photons? Then, Niels Bohr used the same idea to explain why electrons in an atom can only be in specific orbits. And then, finally, this guy Louis de Broglie came along and flipped the entire thing on its head. He asked a crazy question. If waves can act like particles, could particles also act like waves?
And de Broglie's idea was the missing piece. He realized that if an electron is a wave, then the only way it can have a stable orbit around a nucleus is if a whole number of its wavelengths fit perfectly around the circle.
It has to wrap back around on itself and create a stable, standing wave. If it doesn't, it just interferes with itself and disappears. This is the physical reason for quantization. It's not a trick, it's just the wave nature of matter.
Okay, so this whole particles or waves thing leads us right to the heart of our story. And it brings us to a beautiful and strangely intuitive way of thinking about it, which was pioneered by the physicist Richard Feynman.
So you've probably heard of the famous double slit experiment, right? Where a single electron seems to pass through two separate slits at the same time? Well, Feynman asked, what happens if you add a third slit? Simple. Quantum mechanics tells us you just have to account for the possibility that the electron went through all three paths.
Now just follow that logic all the way. What if you add a fourth slit? A fifth? What if you keep drilling holes until the entire wall is gone? And then you add a second screen behind that one with infinite holes, and a third, and a fourth? The logic is totally inescapable. For a particle to get from point A to point B, even through what looks like empty space, you have to consider every single possible path it could have taken to get there.
This is Feynman's brilliant insight, his sum over histories. He said that to figure out the probability of a particle landing at a specific spot, you have to imagine it takes every path at once. And I mean every path. Crazy paths that go to the moon and back, paths that wiggle and loop, paths that go faster than light. You have to add up a little contribution from every single one.
So if it's taking all these paths, why do we only see one? Well, imagine each path has a tiny little arrow associated with it, spinning like the hand of a clock. For most of those wild, crazy paths, by the time they get to the destination, those little arrows are all pointing in random directions. When you add them all up, they just cancel each other out. That's destructive interference. But, and this is the key, for the paths clustered around one very specific route, all the little arrows end up pointing in the same direction. They add up, they reinforce each other. That's constructive interference.
So, what is this one special path? This path where all the little quantum arrows line up and agree? Well, the answer brings us all the way back to the beginning and explains, well, everything.
It turns out the thing that determines how much each little arrow has spun is that word I told you to remember, action. The classical path that we actually see a baseball take is the one where the action is at a minimum. We call it the path of least action. And why do we see that one? Because along that path, and all the paths incredibly close to it, all those little quantum arrows line up and shout in unison. Our solid, predictable world is just the outcome of this infinite quantum chorus.
And this isn't just some weird philosophical point. The principle of least action is pretty much the deepest, most fundamental law of nature we've ever found. It's the reason the thrown ball follows a perfect parabola. It's the reason planets orbit the sun in ellipses. It is the single mathematical idea that underpins all of classical mechanics, Einstein's relativity, and all of modern particle physics. It's the whole shebang.
So when you hear physicists talking about searching for a theory of everything, what they're really searching for is the one final ultimate equation for action, a single principle that describes every single path that every single thing in our universe could ever possibly take. We're not there yet, but now we know the right question to ask. What is it?